and enjoy.
Thanks, Diego. Hi, everyone. Justin, I'll get you some logos if you need some for the USGS presentation when you have one. So let me share my screen. I'll take you on a walk slightly different than your previous presentations. This will be focused specifically at one hazard, not multi-hazard. It'll be earthquakes, and that's my particular role. Let me share my screen, and I'll get you a visualization here, and go into presentation mode. I'll try. Okay. You see my screen, Diego? Excellent. Okay. Okay, a couple things. My background is earthquake seismology. I'm a coordinator of a lot of the real-time products that come out of the National Earthquake Information Center, which is shown here. This is our response room in Golden, Colorado. I have just noticed a typo on the NEIC there. I was playing with my slides too quickly. Anyway, so I coordinate this real-time products, and we're going to take a look at these and get an overview of how these work and the underlying science, who uses them, and how we interact with those users. Before we get going, it's always nice to have a little personal side of the story so that I don't jump right into the science. So here's my latest exploits. This burro here, Mickey, is a friend of mine's donkey, and a good friend of mine, Ruel Sneeder, on the right there. We both take turns racing with this donkey. It's an endemic sport to Colorado called pack burro racing, and you don't ride the burro, you just run with it. And these are like 10, 15, 20-mile races, and it's entertaining if nothing else. But it's quite a sport. So I thought I'd give you a show of what we do here in Colorado. And you'd think that old guy like me would get worn out from the race with the burro, but here's Mickey after the most recent race, totally tuckered out. So, okay, on to the talk. So I'll give you an overview of the earthquake information products and the underlying science that's there, and the challenges that we have in making these products and just delivering uncertain information. The second element here, I'll only touch on given the time, but basically I'll tell you where we're going in terms of new directions. We have models of what happens after an earthquake, and we're going to be slowly updating those models as time goes on after the earthquake with new ground truth information imagery, and I'll just allude to that towards the end. But in the process of going through these products, what I'll do is describe the range of uses and users, and that really drives what we do, and what formats we deliver, what kinds of products, and then some of the underlying scientific and also communication challenges in trying to deliver each of these products. And when I say we, this is the team that I oversee at the USGS, but we also interact with external partners at universities and different groups around the country, around the world. And our agency also funds external grants that allow us to bring in people from academia and from consultancies to do specific tasks that we don't have the expertise in-house. So we get a lot of collaboration that way, and we get a lot of things done through funding and collaborating with other groups. A little more motivation for what we'll present today. This is some pictures I took after the 2008 Wenchuan earthquake. This was a very devastating earthquake. About 88,000 people were killed, and you can see that the city was destroyed not only from the shaking, but also from the landslides that followed in the area, in these very steep mountains all around. And this is my colleagues, all engineers on the ground after this earthquake, doing some surveys. And here's me and Nico Luco is a structural engineer in the town of Bechuan, trying to get a sense of what was the major source of collapses in the structures and the types of shaking that was experienced. So these things really move you when you see this, and it motivates us to do something, to try to help. And one of the systems that we've developed since is called the Prompt Assessment of Global Earthquakes for Response, or PAGER system. And I'll be talking about this quite a bit more as we go. But basically, the system here is meant to take all the earthquakes that we locate at the NEIC, at the National Earthquake Information Center, and determine their importance in terms of whether they're going to require response. A lot of earthquakes happen here, turn into a category green, and they just are either out to sea or away from populations, and they're not going to be consequential. but other ones are going to be consequential, and we figure out how to do that, and I'll show you how that system works. So here we are trying to get a quick 10 to 20 minute summary of what's happened in these earthquakes, and I'll show you how that works. So at the NEIC, what we're doing is we're bringing in data from around the world. We have thousands of seismic stations coming into our basement from almost all countries in the world. So we're taking that data, we're monitoring the data, putting out magnitude location, and we're also developing, and as I'll show you, a bunch of downstream products that go beyond magnitude location to give more information about the likely outcome of that and impact of those earthquakes. And we're doing research in the process to use that data and improve these products as we go with more more well-developed scientific strategies as we go forward. So what we've evolved from in the time that I've been at the USGS is putting a star on a map with a magnitude location to subsequent years where we put out ShakeMap and Did You Feel It, which are estimates of the shaking intensity and color-coded to the shaking level, as you see in a few minutes, to more sophisticated products that look at infrastructure and deliver content to different users, all the way to planning tools. And now we're putting out maps of landslide and liquefaction probability that allow people to see potentially what these secondary consequences are going to be like for earthquakes around the globe. So we have at NEIC, we have a mandate to do, we basically back up magnitude earthquake information for the country, but we also have a global responsibility, and we're the go-to place for earthquake information around the globe. And some nations can do this on their own, but we do that for the rest of the world that doesn't have that ability. So what we've developed over time is what we call the earthquake information system. And you can think of it as tools that are available before the earthquake, at the time of the earthquake, and then post-earthquake for response and recovery. And the time scale I put on the center here is years before, when we can do planning exercises, scenarios. And this PSHA here stands for probabilistic seismic hazard analysis. That's where we map out the likelihood of shaking around the country. And that likelihood of shaking over, say, the next 50 years is used for insurance products. It's used for building codes and determining where it's safe to build at what level. And so those are very important maps. But we can use those maps to determine what kinds of earthquake scenarios are likely in the future. And with the tools like ShakeMap, as you'll see, we can make estimates of the shaking, and different emergency managers, different utilities, different operators of critical infrastructure can use those scenarios for planning exercises. But my main task is really in this post-earthquake environment, where we look at some of the main tools for responding to earthquakes, and we'll talk about these in some detail. One of the keys, though, is that we do this end-to-end within our own organization. So we determine the magnitude location. That triggers another product called ShakeMap, as you'll see. That ShakeMap is the base layer of the intensity of shaking that gets used to determine whether there's going to be impacts to the earthquake. With the ShakeMap, are there population exposed? Is it a vulnerable population? We can then estimate losses from that. It also is the underlying shaking hazard for ground failure hazards that I'll show you as well. So we're integrating all these systems in near real time. They're feeding each other, and products are updating over time as in the minutes immediately after an earthquake. And this is targeted at a wide variety of users, as you'll see. So we're going to zoom in on the 4 systems that I've played a primary role in developing, and I'm responsible for overseeing their operations and continued development. So these systems, Did You Feel It? I don't know how many of you have felt an earthquake, have been in California, been in an earthquake country, but anyone that feels an earthquake around the country, around the globe, can get in and say what they felt and fill out a few questions, and we can turn that into a color-coded intensity. And we'll talk about the scale in a little bit more detail, but basically it goes from blues to greens to yellows. When you start getting yellows and oranges, you're starting to get damaging levels of shaking intensity. And at reds, you have very, very serious shaking levels. But this Did You Feel It map is generated completely by citizen science, by having people come in and report what they experienced, which we can turn into a shaking level. The ShakeMap is very different. It is a shaking level, also color-coded with the same color scheme, but it's determined by these instruments in the ground. So we have seismic instruments in the ground, And we use those to infer the shaking everywhere with spatial interpolation and all sorts of seismological tools to estimate the shaking. And we map that out based on the seismic instruments in the ground. Now we can actually combine these two tools so that we take the felt reports and combine it with what we know from the instruments to make a better shake map. And as soon as that shake map's available, that goes on to different systems automatically. The ShakeMap goes online on the web, and it's available through web pages, but it's also available through electronic feeds, APIs, and different types of strategies for pulling it over automatically. And people use that for their own systems, but in-house, we use that one for the pager system that I showed you earlier, which estimates the number of fatalities, as you'll see as we get into details, and also the economic losses. And it does that, as I said, by taking the shaking, looking at the population on top of the shaking, and looking at the number of people exposed to the higher shaking levels and estimating losses from that. So that gives us kind of a view of the earthquake from a societal perspective. What happened? Is it going to be a consequential earthquake? What level of response is needed? There's another path that the ShakeMap takes, and that is with ShakeCast system. And this is a system that's run by individual organizations, companies, agencies. In this case, it's the Nuclear Regulatory Commission. And they take the ShakeMap and they look at the shaking level at nuclear power plants, and they have a quick heads up of the shaking level and whether the shaking level has exceeded any levels of regulatory constraints for them, requiring them to inspect plants or shut down plants. So it's used for critical infrastructure. It's used for bridges and overpasses, for departments of transportation, and it's fundamental to understand that group's situational awareness, not the whole society, but the critical infrastructure for a particular group. And these systems, they're different beasts. The DigiFeel is basically a citizen science tool. The ShakeMap is basically a geospatial tool where we're getting seismic stations and we're interpolating the information from the stations to get the best estimate of the shaking. And then Pagers is more or less an engineering tool where we look at the vulnerability of buildings and the societies around the world. And ShakeCast is also kind of an engineering tool where we look at the individual vulnerabilities of structures, infrastructure, bridges, and other critical facilities. Now, the motivation for this is that we have a whole variety of users. This is just some example logos for these different types of system. And the types of decisions that they make range from using it for communicating through the media, through their own emergency management desires, like Caltrans, Department of Transportation in California. But it ranges from everyone from the media to the general public, to financial decision makers, to aid agencies, and critical agencies that respond to earthquakes, like CalEMA, other offices of emergency management. And you could imagine that each one of these has different levels of sophistication and different uses that they have for these particular tools. So we make these things available, and the layers of these information products in a whole variety of different flavors, GIS, KML, all sorts of spreadsheets and things like that to better make these suitable for different types of uses. One of the common uses, of course, is the media. CNN is taken to the ShakeMap and the pager systems. I like the one in the lower left here. This is Arnold Schwarzenegger when he was the governor of California, trying to explain a ShakeMap to a television audience in Southern California. But you can imagine now that we have a variety of users, and we have to simplify the product so that they can be understood and make them understandable with the uncertainties that they have. And I'll show you how we do that. Now, anytime there's an earthquake of significance, anywhere in the country or globally, we make what's called an event page. This is the earthquake event page. This is built on the fly. As soon as the magnitude and location is made, this template is exercised. And as soon as the shake map is generated from the seismic stations in the ground and the shaking levels at each station, that gets added as what we call a card here. These cards are built on the fly, and they get updated as more information comes in. So each of these products then can be linked, and you can follow the information for those products. I tend to go to the interactive map, which is zoomable and allows you to choose which products and which layers to see. And so I'll do that for this magnitude 5.7 earthquake, pretty much just glancing blow of Salt Lake City, Utah, back in 2020, in March 18. We'll go into the interactive map, and you can see I'm going to layer on layers that are shown on the upper right. The contours represent the shaking intensity with the scale that's shown. And so these yellows and pale oranges are the beginning of shaking levels that cause damage. And this event actually caused probably tens of millions of dollars worth of damage. There were no fatalities, there were no major injuries, because the shaking level was strongest at a kind of a glancing blow to Salt Lake City. And as a magnitude 5.7, it's not that big an earthquake. It's a moderate size earthquake, but it did enough damage to get people's attention. The other thing you can add right away is the population. And if you look at the population here with respect to the strongest shaking, you can see what I mean, why this could have been worse if it was just centered a little bit further to the right. The other thing is that the shaking pattern is complicated, even for a moderate size earthquake. Larger earthquakes have much more complicated shaking patterns. And it's not something that you can infer ahead of time. You have to capture that shaking with these seismic instruments and the felt reports that I'll show you. And so, every earthquake's a bit of a surprise, and these products there capture what happened as quickly as possible, allow people to make decisions based on that. So now I'm going to add another layer, and that's the felt reports. So you see the population. In the population, the number of people are responding through the Did You Feel It system, and we map these out in 1 kilometer boxes, and we average the responses to the felt reports. And you can see the correspondence of the shaking levels with the felt reports and the instruments pretty well. And that gives us confidence that the humans are giving us the same information that we are from the seismic sensors. One thing that the sensors are limited to is just the locations where they are, and the population is obviously much more distributed, and we can get information everywhere. What we developed to use both these felt reports and the seismic instruments in the ground at the same time was the instrumental intensity scale. And basically what we record of the ground is the peak acceleration of the ground. That's a level of shaking in percent G. As you get to these red levels of shaking, high intensities, intensity 9, you're getting to 100% G, which means if you had a vertical acceleration of 100% G, you can throw rocks up in the air. The acceleration is usually horizontal from earthquakes, the strongest acceleration. So 100% G, this intensity 9, is like taking a building and turning on its side for a second and bringing it back. So you think of what kind of buildings would be able to handle that. A brick building, probably not. A wood frame house, maybe. But that's what happens at the highest level of shaking. At the lower levels, you could see that's weakly felt, lightly felt, light, moderate shaking, and potential damage. And you can see how this grows with the different levels of acceleration. So we record the acceleration of the ground and the velocity of the ground, but we convert it to this color-coded intensity that allows us to connect it to this perceived shaking potential damage. With the felt reports, we get the top layers, which is the damage experienced or this perceived shaking, and we can then estimate what the ground acceleration is from the humans. And so this circular system allows us to take advantage of both the data sets and map them together in one particular scale. And that's extremely helpful because we can go back in time and look at historic earthquakes and look at what people experienced and assign intensities and get a sense of what the shaking levels were for those past earthquakes. My son and I actually developed a Twitter intensity scale. It's not published. It's unpublishable, but you can see the Twitter abbreviation here is what the heck. I don't know what some of these symbols mean. He put those on there, so I have no culpability here. So back to this earthquake. There's other things that we've added recently. This, as I mentioned, these products are evolving with time. We're getting new science. We're getting new tools. This ground failure product is really neat. It's only a couple years old. And it's color-coded to green, yellow, orange, red. And green means it's not a problem. Yellow means it's starting to be problematic. And it tells us about the landslide possibility and the liquefaction probability. Now, liquefaction is where the soil actually liquefies because of the shaking level. The groundwater percolates through this typically sand, and it can't hold strength anymore, and it damages structures that are there. And so it's very problematic. And of course, landslides, as I showed you in the first slides of the Wenchuan earthquake, can be very, very problematic. So we have now layers that we can add to these maps that are color coded to the likelihood of having liquefaction in this case, or landslide probabilities. Now, you can see here that the probabilities of liquefaction are strongest in the area that shakes the strongest, obviously, but also in areas that are close to the Great Salt Lake, where there's a higher water level, and in areas where it's flat and there's sandy materials. If I showed you the map of the landslide probability, it's very, very low. It doesn't even show up because the strongest shaking is in flat areas. If the strongest shaking was in the mountains, would have severe probabilities of very high probabilities of landsliding. So this tells us that landsliding is not a problem in this earthquake. The shaking is a problem. There's going to be some liquefaction, but very moderate levels of liquefaction. If this was a much bigger earthquake, not only would you have a larger footprint of stronger shaking, but you'd have more landslides and more liquefaction to contend with as a response. So we can actually look in time at the felt reports that come in over the minutes following that earthquake. We get most of our reports within the first hour, so it's very informative. There's a bit of an interesting problem with earthquakes, and that is in the epicentral area, things are slower, as you might expect. People that shook harder aren't responding as quickly. And in this case, they actually lost power in the epicentral region for some time. So if you look at the responses over time, you can see that we have this kind of donut hole where the strongest shaking was, and that remains until much later when we start to fill in that gap. But knowing that, we've actually worked with, sorry, I got text messages coming off, probably earthquakes. We worked with ARES, which is Amateur Radio Emergency Services, to actually get to our Did You Feel It forms through their radio hub, and they don't need to use the local power or the local communications. They can do this all through email. It's actually radio email. And then we get the reports from ARES. And we've set up with a colleague of mine that is a amateur radio operator, a Did You Feel It wind link, which is their communications platform, to do the Did You Feel It form right after an earthquake anywhere in the country where there's many ham radio operators that are in urban areas that can respond and do contribute to response. And we published an article about this just recently. But back to that Utah earthquake. So this is the pager, what we call a one-pager. It's a one-page summary of the earthquake for that particular event, with estimated fatalities being very low. There were no fatalities, and we estimated there's probably not going to be fatalities. There's always a chance that you can have some fatalities. And this pager system allows us to look at the uncertainties. I'll show this a little bit more detail in a minute. But these histograms tell us, that the color coding is based on the largest value, the median estimate of economic losses, in this case, between $10 and $100 million. And the histogram tells you the likelihood of being in adjacent ranges of losses. These are very uncertain, but they're still very useful because we can give you a ballpark estimate of what the losses are going to be, both from fatalities and from economic losses. And the alert that we notify people on is the higher of the two alerts based on this color coding that we've shown. So this is how the pager system works. And I'll show you a little bit more how it's generated. But basically, we're looking at the population in thousands at each intensity level. If this was a larger earthquake, we would probably have higher shaking levels and potentially populations at those higher shaking levels. And that would have led to higher economic losses and also likely fatalities. So this was, again, a near miss and a moderate sized earthquake, but tens of millions of dollars worth of actual losses. We have a new product that we're just working with FEMA on. And what we do with FEMA is we take our ShakeMap and hand it over to FEMA, and they run it through a software package called HAZUS, which you might have heard of. And it's Hazards US, and it takes the ShakeMap as the shaking layer, and it estimates building damage, the number of buildings that require tagging, green, yellow, and red tagging for whether they're safe to occupy or not. And it gives us estimates of losses at the county level or even the census tract level that we can then put out. With the pager system, we're only comfortable with giving the total losses and the uncertainty of the total losses. But with the more sophisticated HAZUS tool, we can generate more detailed information that's more spatially rich. The catch is that HAZUS is only running in the US, so we can only do this for domestic earthquakes. So internationally, the pager system is the only thing that we have to rely on. And it's, again, it's a general tool, but it's very important for a heads up of whether this is a green, yellow, orange, or red earthquake for response purposes. Now, did you feel it is felt? We get responses all over the country. And one thing we've known for a long time, and that's really shown quite nicely in this image, we have 2 magnitude 6 roughly earthquakes, 5 slightly smaller earthquake in Mineral, Virginia in 2011, and the Napa Valley earthquake. And you can see that the intensity reports for California are over a much smaller area than they are for the earthquake in Mineral, Virginia. But we've known this for a long time. Energy travels much more without being impeded in the east than it is in the west. The west has many more faults. It's a hotter, more absorbent crust than it is in the east. And so the same size earthquake is felt and can be damaging over a much larger area than it is in the west. And this is simply borne out by the felt reports that we got over the course of these 2 events. But we can also look back in time. The system's been running for about 20 years now. This is 2016, and you can see that the central east US is really dominating shaking, and that's because of induced earthquakes due to wastewater injection from mostly petroleum exploration. But you could see California and the Pacific Northwest lighting up as well. And over time, if we look at 20 years completely, we start to see the pattern of earthquakes that happen over a longer time period in the United States. Although larger earthquakes happen at much less frequent time periods than 20 years. And so there's a lot missing. But this map of what's happened in the last 20 years starts to reflect what we think will happen over the long term. This is that probabilistic seismic hazard map that I mentioned that drives the building codes, that drives insurance policies, and a lot of decisions about critical infrastructure and other things. So over time, we expect that the felt reports and the earthquakes will reflect what we anticipate to happen, but we never know where particular earthquakes will happen or when they will happen. Globally, we get a lot of felt reports. We have now over 6 million felt reports for earthquakes around the world, and it's pretty impressive when we have events to get these types of reports, and it really helps us constrain the shake maps. And we get those from most countries. There's another group of users, though. In terms of social science, these reports include first-person accounts. The DigiField data, we have questions that people answer, and we assign intensities based on those questions. But then they can write down what they did and what actions they took and how they feel. And we've had a number of social science looking at those data to try to understand people's behavior from earthquakes. I'll skip that. So one thing we've done with the ShakeMap system is to make shake maps. We've been doing this for the last 20 years, but we can go back in time, and we can go back to pretty much the turn of the century, 1900, where we can use the intensities that were reported and the damage reports, as I mentioned, to assign intensities and make shake maps from them. And so now we have over 120 years of shake maps, which we can use to calibrate losses based on what the actual impact of those earthquakes were. So this is the maximum shaking all over the world based on the shake maps in our, what we call the ShakeMap Atlas. And these are made up of many, many earthquakes, as you can see. And I'll skip this. This atlas now has, as I mentioned, over 14,000 events. You can search these by year and look at these different shake maps for anything that's happened over this 120-year period. And as an example, the great 1906 earthquake, we can make a shake map of, because we have nearly 1,000 intensity reports based on the observations that are preserved in newspapers and historical documents for the time. And we can make a pretty darn good shake map with that. So with all of these shake maps, let me, I added an extra slide here. I'll skip that. I got a little out of base here. So I'll come back to this, but with all these shake maps, we can develop a loss model that we use in the pager system, and I'll show you how that works. One of the other users of the shake maps, the real-time shake maps, they come out in about 5 to 10 minutes and maybe up to 20 minutes around the world, is financial decision makers. And so there's a number of new insurance policies that are actually based on or constrained by the shaking level that comes out of the USGS shake map. And in fact, there's things called catastrophe bonds, CAT bonds, that are basically determined whether the insurance policy gets paid out, whether the ShakeMap is a certain level and a certain population exposure, and if so, the policies get paid. Rather than spending months and years to survey all the damage and to look at filed claims, they can actually pay out financially within a day or within 3 days of an earthquake. And that makes it much easier to respond to earthquakes and to rebuild and to recover. And there's a whole class of different financial products that work this way. And I have a couple papers that describe this if anyone is interested in it. But it's a very important aspect of the ShakeMaps. This financial use community is actually doing a pretty good thing, which is it's transferring the risk for those that need insurance and need coverage after a disaster, and making it much easier to pay out at a cheaper rate than it would be with conventional insurance policies. And they like this USGS ShakeMap because it's independent of, we just do it based on the science and based on our data that we collect. And we don't really care about the outcome. We're just trying to make the best ShakeMap. So we're the independent information that they use to trigger these different types of insurance products. Now I mentioned, let's see how we do it. Now I mentioned ShakeCast. I'll go over this very quickly. So ShakeCast, in this case, is a system that's run by the state of Utah Department of Transportation. They're running this tool called ShakeCast. It's software that we developed. We give them the software, and they put in their bridge locations and the structural elements of those bridges, and they take the shaking off the ShakeMap and estimate the likelihood of damage to each bridge. And it gives them this report instantaneously of the likelihood or the inspection priority, the likelihood of damage, or how they call it inspection priority, for each of their overpasses. And that happens within a minute or two of the ShakeMap being generated. So 5 to 10 minutes after an earthquake. This automatically goes out to the different inspectors in the Department of Transportation, and it gives them a situational awareness for the first few hours and even the first day or two after a significant earthquake. It's also very important when there's a moderate sized earthquake, they know that they don't need to respond to certain areas, and they can focus their attention on the few bridges that might have been shaken. So for that Magna, Utah earthquake, the 5.7, there's a number of different groups that were running the ShakeCast system. The Federal Highway Administration, the Veterans Affairs has their hospitals in the ShakeCast system. FERC is a Federal Emergency Regulatory Commission. They have power generating dams, and so they have to decide whether to inspect dams. The U.S. Bureau of Reclamation also has dams. The Department of Interior is USGS's agency, and looks at our infrastructure as well. And so there's a number of different groups that have situational awareness based on the ShakeMap by running the software and having their inventory in their own instance of the ShakeCast software. And there's quite a wide range of different user categories, and you'd expect some of these, but others might be surprising. Education, LA Unified School District has 800,000 students. They've got thousands of buildings, so they want to know what they can do after an earthquake. And school buildings actually become Red Cross shelters in some situations. So they need to know what bad happened, but also what things are accessible. And you could imagine businesses could take advantage of this, and other lifelines, critical users, transportation, as I mentioned, et cetera, et cetera. And the key ingredient to be able to use ShakeCast is you have to know for each structure, given a certain shaking level that comes off the ShakeMap. In this case, we have different parameters: acceleration, velocity, intensity. But for each level of shaking, you have to know the likelihood of having slight, moderate, or heavy damage. And that's what comes out of what we call a fragility curve. These curves, engineers have a good assessment of these for their own structures. They can put that into the ShakeCast system. And when they know a certain shaking level at that facility, they can estimate the likelihood of damage. I'll skip over that. One of the key users is the California Division of Safety of Dams. Normally, and currently up to very recently, most critical lifeline groups would take the epicenter, draw a circle, this black line around it, and inspect everything in that circle. That circle would be bigger for larger magnitude earthquakes, and they would inspect all facilities in there. With the ShakeCast system, they actually now only need to inspect the ones that are shaken at a level that causes concern. And so it reduces their inspection area in this particular magnitude 6 earthquake in north of San Francisco. But the real benefit comes when you have a major earthquake. So this dashed line represents the San Andreas Fault, and the gray represents the shaking that we would estimate from a 7.8 magnitude earthquake along that fault. And normally they would draw a circle around the epicenter and inspect all the dams within that circle. But with the shaking estimates and with the knowledge of the locations of the dams, the ShakeCast system gives them a much more detailed area of inspection and priority of inspection of their dams. Now, I showed you that long San Andreas Fault. The length of the fault is extremely important, and the dimensions of the fault for the shaking. So this shake maps for 3 different size earthquakes, magnitude 6, 7, and 8, all on the same map scale. And for a magnitude 6 earthquake, the fault might be 10 miles long, 15 kilometers, maybe 40, 50 kilometers for a magnitude 7, and then potentially hundreds of kilometers for a magnitude 8. And it's very important to establish the dimension of the fault because the shaking is going to be strongest along that fault. If we have seismic stations everywhere, we capture that shaking. But if we don't have stations everywhere, we want to determine the fault location as quickly as we can and use that to inform the shaking as well. So that magnitude 7.8 San Francisco earthquake, the fault is actually this black line in here, and that's over 400 kilometers long. The shaking along that fault is obviously very, very strong, and that's where the majority of the damage is going to be. So we could take all these historical earthquakes and we could look at the shake map, generate shake maps for those, look at the population at the time of the earthquake, and we can get the database, to build a database of the fatalities and the economic losses from each earthquake. And what we can do from that is build a curve for each country that shows for each intensity level, what fraction of the exposed population is likely going to be killed. So for California, where there's very, very well engineered and very well built houses, it's a very small number, maybe 1 part in 10,000. But in Iran or in China, it's almost 10% of the population in the strongest shaking level, intensity 9, will perish because of the types of buildings that are there. Very heavy, typically adobe structures that when they collapse and do collapse easily are very deadly. And so we've developed these curves for each country, and that allows us to do what Pager does, which is to take the shaking map, look at the population exposure, and use the country model for vulnerability to see what the likely outcome is in terms of fatalities and economic losses. Again, that's a pretty uncertain process, but we've calibrated against past earthquakes, and it's very useful, although it's uncertain, and we provide those ranges of uncertainty in the histogram that we show. So this is the actual way that's portrayed, and we can provide the uncertainty as the probability of being in adjacent ranges of fatalities that are a factor of 10. Same thing with economic losses. So I already showed that. So around the world, we have earthquakes. Domestically, we have very expensive earthquakes in California because the structures are built so well. There can be fatalities, and there will be in the future in California, but they'll be low compared to other places around the world. And for significant earthquakes around the world, we generate these alerts and we send this out to a variety of different users, and they go online immediately on our web pages. But USAID is one of our funding agencies that support the development of this. And USAID is the Agency for International Development that sends out response in terms of urban search and rescue teams, but also financial assistance after disasters around the world. So they have a hard time taking a magnitude and epicenter and saying what to do. So we make the shake map, we generate the page results, we send them these alerts, and they have a heads up very quickly about what the overall impact is going to be, and they can start their appropriate response based on the level of the impact. And the details here, as we talked a little bit earlier, that you have the population exposed at each intensity level, and then the information about losses and more information that's typically used. Let's see how we're doing on time here. Okay, I better wrap this up pretty quickly. Importantly, the pager users are a whole variety of different groups, as you might expect: nonprofit organizations, humanitarian assistance, response. FEMA uses this domestically. INSARAC is the consortium of urban search and rescue teams around the world. and then a lot of government agencies, financial groups, as I mentioned, and other risk analysis, as well as the media. So this goes out automatically. These one-page summaries get sent all over the world and redistributed to our web pages. I think I'll just skip over this part really quickly. As I mentioned, that Wenchuan earthquake had about 20,000 fatalities due to landslides alone. And so we really want to determine which earthquakes are going to have additional problems due to landslides or liquefaction. And that's where this ground failure product comes in. And that 1906 earthquake, we're not immune to these problems, and we will see that in big earthquakes domestically. So we've developed this ground failure model that now shows up. And for this particular earthquake in Papua New Guinea, the ground failure for landslide and liquefaction were red levels of alert. And the ShakeMap and the probabilities of landslides is really high where there's strong shaking in very steep slopes. And this earthquake had just catastrophic ground failure that resulted in transportation problems and response problems, in industry being lost, and it actually affected the country's GDP significantly because of that. So there's a lot more to the story, but I think you've got a good sense of what's possible with these systems. And I'll kind of leave it at that and see if you have questions. But you can see there's a lot of challenges. There's a lot of uncertainty when we have the shaking. We don't have constraints of shaking everywhere. When we look at the population exposure, those are approximate grids of population around the world. And the vulnerability obviously varies from place to place within countries, but we have to approximate that with a single curve, with the exception of the United States where we have several curves. But there's uncertainties involved with all those calculations that are compounded, and that's why we have this uncertain histogram. But I think these things are still extremely useful for initial decision making, and I'll leave it at that.